All right, in this video, we're going to go over how do we actually calculate a confidence interval for a population proportion of one sample. Okay, so recall from my intro to confidence intervals video, which if you haven't seen that, I'll be sure to put a link in the description below. But the confidence interval for a population proportion is the following. We take our let's get that. We take our sample percentage, our sample proportion, and we add and subtract the margin of error. So what's the margin of error for a one sample proportion? It's going to be our critical z-score times the square root of our sample proportion times 1 minus the sample proportion divided by n. So once again, p hat is our sample proportion, n is our sample size, and z star is our critical z-score, which is based off of the confidence level. Once again, if all of that is new to you, please go back and watch the introduction to confidence intervals video. Just really quickly, remember each confidence interval is generated by a sample. So different samples, every time we get a different sample, we're going to generate a different confidence interval. So whenever we say that we're 95% confident, that means that if we repeat this process, right, if we calculate a bunch of different confidence intervals from different samples, approximately 95% of all of those confidence intervals will contain the true population proportion, okay? Which, by the way, we don't know. We don't know the true population proportion. That's why we are calculating a confidence interval to estimate that. That's actually called what we call inferential statistics, when you take a sample to describe a population. All right, with all that being said, let's get into an actual example here. How do we calculate this? All right, for example, an American insurance company checks police records on 582 accidents and notes that teenagers were at the wheel of 91 of them. The data were collected randomly and from across the entire United States. Okay, so we're going to have several parts related to this information, this question here. All right, first of all, part A. Are we able to calculate a 95% confidence interval for the proportion of all auto accidents that involve teenage drivers? Check the conditions. Once again, I keep referring to this intro to probability video, but remember we're going to use the central limit theorem. I'm going to abbreviate it CLT for proportions. And that tells us what to check for, okay? So the first thing we need to check for is the independence assumption. All right, if I learn how to write here. Oh my goodness. All right, independence, I-N-D-E-P-E-N-D-E-N-C, all right. Independence assumption. All right, do we have independent data values, right? Well, remember the way that we can check that is via randomization. Well, they tell us that the data was collected randomly. So because we have a random sample here, a simple random sample, we can go ahead and say the independence assumption is satisfied, okay? Also, there was a 10% condition. Remember, we need to make sure that we sample less than 10% of the population. Well, we sampled 582 accidents. Certainly, there's way more than 582 accidents across the entire United States. So yes, we sampled less than 10% of all possible values there. And then lastly, we need to check the number of successes and the number of failures, the success and failure condition. To check that, we need to do n times p hat, and we need to check n times 1 minus p hat. And we need both of those to be greater than or equal to 10. Well, what the heck is p hat? P hat, if you recall, is our sample proportion. Okay? And how do we calculate that? We go back to our problem. They told us out of 582 accidents, 91 of them were caused by teenagers. So that is, I like to think of p hat like this. P hat, I like to think of it as x over n. If you're familiar with the binomial probabilities we talked about in previous videos, Basically, you take the number of successes, so to speak, and you divide it by your sample size. Okay? All right, so then what we're going to do is we take x should be 91, and we divide that by, let's double checking the numbers here, 582. Let's see what that gives us. I'm going to take 91 divided by 582. To 3 decimal places, we get a 0.156. Okay? All right. So, but really what we need here is to once again check if the number of successes and the number of failures is greater than 10, right? Well, really, we'll go ahead and do it. If we take our sample size of 582 and divide it by a 1.56, we're going to get close to that 91 number, right? Because there's 91 accidents that were caused by teenagers. So certainly 91 is greater than or equal to 10. Okay? If we were to go over here and do n times 1 minus p hat, that's the number of failures. So really quickly, I'm going to just take 582, subtract away 91, and that'll tell me the number of failures, which is 491. So if we end up taking 582 times 1 minus 0.156, we're going to get something close to, what do we say? 491. And let me prove that to you really quickly. 582 times 1 minus 0.156, and we see that, something really close to 491. All right, so once again, this is just checking the number of failures and the number of successes. Both of those are greater than 10, so the failure and success condition is met. So can we perform a confidence interval? Yes, we can. All right, so that's how you check your conditions. Check for randomness, check for the 10% condition, and then check for the number of successes and failures are greater than or equal to 10. All right, now they want us to calculate the confidence interval. So I'm just going to rewrite our formula here. Our confidence interval is equal to all right, let's make sure I can write here. Confidence equals, we take our sample proportion p hat and we add and subtract the margin of error. Well, what's the margin of error? The margin of error is our critical z-score times the square root of p hat times 1 minus p hat over n. Remember the p hat times 1 minus p hat over n, square root of that, we call that the standard error. Okay, so just filling this into our formula. Let's see here, z star is the square root of p hat 1 minus p hat over n. Okay, so we have already calculated p hat. I'm going to bring it down. It's a 0.156. So our confidence interval will be a 0.156 plus or minus z star, the critical z-score. We need to be 95% confident. So that means that our z-score is going to be a 1.96. Okay? Really quickly, how do we get that? You guess what I'm about to say. It's in the video before this, Introduction to Confidence Intervals. But what we have here is a standard normal distribution of z-scores. Right down the middle is z equal to 0, and then on both the left and right side of that equal distance from that 0, we have a negative z critical and we have a positive z critical. The area shaded in between them is the confidence, right? We are 95% confident, so all of that shaded area is 0.95. The remaining unshaded area, which is 0.05 in this example, is divided by 2, and that is the area that goes in the left and right tails. So here we go, 0.05 divided by 2, that gives us a 0.025. And for that same reason, 0.025 in the right side. So the way that we found this z-score here is we just said, let's find the negative one, and then our answer will be the positive version of it. So we go to our z-tables and we do a reverse lookup. We find the z-score that has the area the closest to a 0.025. So let's see here. Do I have some z-tables? I do. So we go here, and we see right here, we have a 0.02500. So what's that z-score? It's a negative 1.96, which indicates the positive version is just exactly that, the positive version. So that's where we get the 1.96 from. Okay, then this is multiplied by the square root of 0.156. And I'm going to erase this to give myself a little bit of room here. Let's see here, times 1 minus 0.156 divided by n, our sample size, which was 582. All right, remember n is 582. Okay. All right. So now, doing that will give us an answer here. So our confidence interval equals 0.156 plus or minus, let's go to our calculator to calculate our margin of error. Okay, so I take my 1.96 times the square root of, I'm going to write it like this, 0.156, open parentheses, 1 minus 0.156, close parentheses, and still underneath the square root, I divide that by 582. Okay? Everything's underneath the square root. We hit enter. Into 3 decimal places, we get a 0.029. 0.029. All right, so that means that our confidence interval, so if the question asks you what's the margin of error is a 0.029. But what's the actual confidence interval? What we do is we take a 0.156 and we subtract away 0.029. So 0.156 156 minus a 0.029. That will give us a lower bound of 0.127. And we add, we add that. So let me go in here. Let me delete that, change it to a plus. 0.156 plus 0.029 will give us an upper bound of 0.185. All right, so there we go, folks. That is our 95% confidence interval. It goes from 0.127 or 12.7% up to 18.5%. Okay, y'all about to be really mad at me, but let me show you how we can quickly do this in Statcrunch. If you want to know how to do this in your TI-84 or 89 calculator, feel free to shoot me a quick email. But this is how you do it in Statcrunch. Really straightforward. Notice here, how do we calculate our p-hat? We took x divided by n. We took 91 divided it by 582. Keep those numbers in mind. All right, so in Statcrunch, we go to Stat. We go to Proportion Stats. Proportion Stats. Let me see, here we go to Proportion Stats, and then we select one sample because we only took one sample with this, okay? And then very important, we're gonna do this with summary. We don't have the actual data, all we have are the summary statistics. So we're gonna click with summary. Okay, the number of successes. That is your X value that we just used to calculate our p-hat, right? It was 91 out of 582. So the number of observations, that's your sample size. Okay, very important. Next group is we have to decide, we have to tell the calculator what we're performing, okay? We will talk about hypothesis testing later on in this semester, but right now we are doing a confidence interval. So select the confidence interval and then look at your level. We want to be at a 95% confidence level. So that's why our level is a 0.95. We are at 95% confidence. Keep your method as standard. That's what we're using. We go to compute. And I'm hoping you guys can see that. If we look here, look where it says L limit. Your lower limit is a 0.127 and your upper limit is a 0.186, just like we've calculated. Okay? All right, so that's a quick way of getting your confidence interval in Statcrunch, if you so choose that way. All right. Explain or interpret what your interval means. What's the interpretation here? This is kind of the standard way that we interpret the confidence intervals. We say this. We are 95% confident that the true population proportion of all accidents involving teenagers is between, and you just grab your lower limit and your upper limit, a 0.127 and 0.185. That's it. It's very important, guys, that you say that you are 95% confident. Do not say there is a 95% chance that the population mean is between 0.127 and 0.185. Don't ever say that. So we say we are 95% confident that the population proportion of all accidents involving teenagers is between 0.127 and 0.185. Okay? We'll look at part D. All right, well, what does it mean to be 95% confident? Okay? 95% confident means this. Let's write it this way. 95% confident means that 95% of all confidence intervals generated by samples of the population will contain the true population proportion. So as we said at the beginning of this video, each sample that we take is going to generate a different confidence interval. So let's say we take all possible samples from the population. We got all these different confidence intervals, all of these different lower and upper bounds. Well, 95% of all of those confidence intervals will actually have the true population proportion somewhere in there. Okay? That's what it means to be 95% confident. I know it sounds similar to saying there's a 95% chance that the population mean is in our generated confidence interval, but no, this is saying something slightly different. So I hope that clears what it means to be confident to a certain degree. All right. A politician urging tighter restrictions on driver licenses issued to teens says in 1 of every 5 auto accidents, a teenager is behind the wheel. Does your confidence interval either support or refute this politician's statement? Well, remember our confidence interval went between, let's grab it. It went between 0.127 and 0.185. Okay? The politician is claiming that 1 out of every 5 auto accidents is caused by a teenager. 1 out of 5, if you go to your calculator, it's 20% or 0.20. Well, if we look at our 95% confidence interval, we do not see 0.20 being within that interval. 0.20 is outside of that interval. So what we can conclude is that it's unlikely that the politician's statement is correct. Okay, that's because 1 out of 5 or 20% is not in our confidence interval that goes from 0.127 to 0.185. So we are refuting his statement. We're saying his statement is not true, or at least is very unlikely to be true. All right. Here we go. Calculate the 99% confidence interval and compare it to the 95% confidence interval. What do you notice? Okay, so the 95% confidence interval we've already done. That was from 0.127 up to 0.185. Well, what will the 99% confidence interval look like? Okay. Well, to calculate this, I am going to use Statcrunch. But if you want to do this by hand, let me see here. If you want to do this by hand, let me give you your critical z-score. Your critical z-score should be, try using a 2.55. All right, so try using that and see if you can get something similar to what we're going to calculate. Now, you'll be a little bit off. It'll be a little different because of rounding, but you should be close. But for everyone else that wants to use Statcrunch, remember our X value was 91, our N was 582. And by X, I mean the number of successes. Okay, so we're going to go back to Statcrunch. Okay. Let me see. All right, there we go. We're going to go back to Statcrunch. Going to minimize that. Let me bring my mouse over. All right. So I'm going to go to Stat. We go to Proportion Stats, one sample with Summary. Okay. Our number of successes, 91. Number of observations, 582. We are doing a confidence interval. But this time, our confidence level is 0.99. We want to be 99% confident. Let's go to Compute. And if I could drag it over, there we go. Our lower limit is a 0.11, let's say 0.118 to 0.195. All right, that's the 99% confidence interval. So what happened? What do we notice? Notice that for the 99% one, notice that the lower bound is a little lower and the upper bound is a little higher, aka we have a wider interval. So what do we notice? We notice as the confidence level increases, the confidence interval becomes wider. Okay, so I hope that makes sense. What I mean by wider is that the lower bound becomes a little smaller and the upper bound becomes a little larger. Okay, almost there. Here we go. I believe this is the last one, folks. To be within 1% of the true population proportion with 95% confidence, how large of a sample size should we have here? Okay, the key here is to be within 1%. That's our keyword. To be within 1%, they are talking about the margin of error. Okay, so they're telling us that our margin of error is 0.01, is 1%. And we want to do this with the true population proportion with 95% confidence. So that tells us that our critical z-score has to be 1.96. Once again, feel free to go back in the video and see where we calculated the critical z-score for 95% confidence interval. So now what does that mean? So let me just write down the formula for our margin of error. So our margin of error equals, it is z critical times the square root of p hat times 1 minus p hat over n. Okay? All right, so I want to solve for n, basically, because I know everything else. I know my p hat. Okay, in fact, let's go ahead and write that down. Remember, p hat is 91 out of 582, which ends up being a 0.156. I know my n is, or I know my z star, and I know my margin of error. It's just a matter of me solving for n. So what I'm going to do really quickly is we're going to go through some algebra here, and we're going to solve this equation, the margin of error equation for n. All right, so the first thing I'm going to do is I want to get rid of that square root on the right side of my equation. I'm going to square both sides of my equation. Okay, so the right side becomes the margin of error squared equals, whenever you have something times something else and you want to square it, you can square each individual component. Okay, so just don't fret about the algebra. We'll get to the final answer in just a second. When I square the square root, it cancels out the radical, so we're left with p hat times 1 minus p hat over n. Okay. Next thing I'm going to do is I'm going to multiply both sides of the equation by n. Okay. So on the left side, we have n times the margin of error squared equals our critical z-score squared times p hat times 1 minus p hat. And the last step is divide through by n. Or excuse me, divide through by the margin of error squared. And that will give us our formula. Okay? So to find the sample size needed to achieve a certain margin of error, this is the formula. N equals your critical z-score squared times your sample proportion times 1 minus the sample proportion over the margin of error squared. You don't have to worry about all that algebra, folks. Know that that is the formula. Okay, once again, this is the sample size needed to achieve a certain margin of error. Okay? All right, now we have everything we need. Just plug it into the formula. Let's go n equals, let's go a different color here. Our critical z-score was 1.96. We square it up times our 0.156 times 1 minus 0.156 divided by the margin of error squared. We have to be within 1%, so we're going to square 0.01. All right. Let's go to our calculator. Okay, so it's going to be 1.96 squared times 0.156 times 1 minus 0.156. Okay, and then all that's going to be multiplied and is going to be divided by 0.011% squared. Okay, and if you write it like this, the calculator will do the correct orders of operations, and we get 5,058.004. Uh-oh. What you should do, that should be an 8 here. What you should do in this case, folks, is always round up. So you're going to always round up your answer to the next whole number. And so that's why our answer is 5,059. That should be our minimum sample size. So that should be the sample size we take in order to get within 1% of the true population proportion. Okay, I know that was a heavy one, but I hope you guys find that useful. And I look forward to seeing you in the next video. All right, see you then.